Here in Chapter 2, we will define our trig functions in a little bit different way than we did in Section 1.3. In Section 1.3, we use a point on the terminal side of the angle to define our trig functions. You can see down here in the box we had y divided by r divided by y, and everything was in terms of x's and y's relating to the point that we picked on the terminal side. Here in this section, we will define them in terms of solely the right triangle itself. So here is our angle A, and looking at our angle A here in standard position, we really want to work with the right triangle that is formed by using the point that we picked on the terminal side and using the distance in the y direction and the x direction, and our r, the distance from the point that we picked to our vertex. We wanted to work with in terms of this right triangle. So if this is my angle A that I pick, we know that sine is y over r. Well, y would be the side that is opposite, meaning not touching the angle, so it's opposite of the angle. And our hypotenuse, of course, is the side that is across from our right angle. So r would be our hypotenuse. So since sine was defined as y over r, we are now going to define it in this section as the opposite side of the angle divided by the hypotenuse. Also, for this angle, we will have an adjacent side. The adjacent side will be the side that is touching the angle. So the side that is adjacent to angle A will be our x distance. So cosine we defined as x over r. Well, in this section we're going to look at it as the side that is adjacent to angle A divided by the hypotenuse. And tangent now will be the side that is opposite of the angle divided by the side that is adjacent to the angle. And of course we have all of our reciprocal functions defined in a similar manner. Here in example 1, we will use our new way of defining trig functions to solve for the sine, cosine, and tangent of both angle A and angle B. So let's start with our angle A. So we want to find sine of angle A. So here's my angle A. We want to identify the side that is opposite of our angle A, and that would be right here. And the side that is adjacent to our angle A would be right here, the side that is touching our angle A. The side that is across from our right angle is always the hypotenuse. Now we have all three sides labeled, and we can now form our trig functions. So sine of angle A would be the side that is opposite divided by the hypotenuse. So that would be 36 divided by 85. Cosine would be the side that is adjacent divided by the hypotenuse. So that will be 77 divided by 85. Tangent will be opposite over adjacent. The opposite would be 36, and the adjacent side would be 77. Here's where the words SOHCAHTOA come in. If you use S to mean sine, so this would be our SO, O-A, O-H, that's our SO. Ka, so that's cosine, and then adjacent hypotenuse, and then TOA, that's the T for tangent, and then the O and the A for opposite over adjacent. Alright, now for sine B, cosine of B, and tangent of B, we are going to work from the angle B this time. The hypotenuse will stay the same, because that will still be the side that is across from our right angle, but this time we're going to work from the perspective of angle B. And now, going across, 77, this side will now be the opposite side, and our adjacent will be now the side that is touching angle B. So sine of angle B will be opposite over hypotenuse. So now the opposite side will be 77, and our hypotenuse is 85. The cosine of angle B will be adjacent over hypotenuse, and that will be 36 divided by 85. And tangent of B now will be opposite over adjacent. So the opposite side 77 and our adjacent side 36. One thing that we notice is since we're working within the same right triangle, that sine of angle A is the same as the cosine of angle B. And the cosine of angle A is the same as the sine of angle B. This is something that we will work with in the future called cofunctions. We just want to observe for now that those are similar values. Suppose ABC is a right triangle with sides of length A, B, and C with right angle at C. Here we are given capital A, capital B, capital C to represent the angles of our right triangle, and lowercase a, b, and c to represent the sides of our right triangle. And it tells us that our right angle is at C. So let's draw a picture here. Here's our right angle. We will call that angle C. Let's call this angle A and call this angle B. It doesn't matter the order of angle A and angle B. And now we're going to label our sides. And traditionally, across from angle A, this would be what we would call side A. Across the opposite side for angle B, we would call that side B. And across from angle C, we would call that side C. So we are told that side A is 6 units long, side C is 7 units long, and we are told to find side B using the Pythagorean theorem. So our Pythagorean theorem would be a squared plus b squared is equal to our hypotenuse c squared. So that would be 6 squared plus b squared is equal to 7 squared. So we get 36 plus b squared is equal to 49. And I want to subtract 36 from both sides. We get b squared is equal to 13. And now I want to take the square root of both sides. So we get that b is equal to the square root of 13. Now we know our sides of our right triangle, and we want to form the sine, cosine, tangent, and the reciprocal functions. We want to form those function values from the perspective of angle B. So sine of angle B, we need to find the opposite over the hypotenuse, and the side that is opposite of angle B, since we're working from the perspective of angle B, we found that to be the square root of 13. So that would be the square root of 13 divided by the hypotenuse, which is 7. For cosine of B, we want adjacent over hypotenuse. And the adjacent side would be the side that is touching B. That would be side A, which is a value of 6, divided by our hypotenuse, which is 7. And tangent would be opposite over adjacent. And the side that is opposite would be square root of 13, and the side that is adjacent would be 6. So we have sine, cosine, and tangent of angle B. Now we will, it should be square root of 13 up here for sine. So now we will take the reciprocal of our sine, cosine, and tangent functions. So cosecant of angle B Well, sine was square root of 13 divided by 7, so cosecant of angle B will be 7 divided by the square root of 13. And we talked about we want to rationalize, we want to get rid of that radical. So we'll multiply top and the bottom by the square root of 13, and that gives us 7 times the square root of 13 divided by 13. Secant of angle B will be the reciprocal of cosine, so that would be 7 divided by 6. And cotangent of angle B will be the reciprocal of tangent, so that would be 6 divided by the square root of 13. And once again, we want to rationalize our denominator. Multiply top and the bottom by the square root of 13. And we get a cotangent value of 6 times the square root of 13 divided by 13. There are 3 special angles that we want to be familiar with, and we want to be familiar with all of their trig function values. And those special angles will be 30 degrees, 45 degrees, and 60 degrees. We will have to memorize all of the trig function values of these 3 angles. Now, instead of just rotely memorizing them, we can actually develop what we call our special triangles to help us develop all trig function values for these 3 special angles. In order to do that, we're going to start with an equilateral triangle. In this equilateral triangle, we'll have all of the same angles of 60 degrees and all of the same sides of 2. And what we're going to do is we're going to take this equilateral triangle, I'm going to cut it right down the middle, we're going to cut it in half. Now when I cut it in half, what happens is that we get, and let's look over here, we get 30 degree, 2 triangles where 30 degrees at the top, so we split that in half, so that's 30 degrees each. And down here we still have 60 degrees, and then here, because we cut it straight down, we have a 90 degree angle for both of these triangles. Now we're just going to pay attention to one of them, so I'm going to redraw one of them right over here. This is what we call our 30, 60, 90 triangle. And the hypotenuse for this will be a length of 2. That's the longest side of our 30, 60, 90 triangle. And if I look down here by the 60 and 90 degrees, we have a length of 1. Now we want to know what is the length of that third side. So we can use the Pythagorean theorem to develop or to find the length of that third side. So we already know the hypotenuse, so we're looking for 1 squared plus, let's call that x, since we don't know it, x squared is equal to the hypotenuse squared. So that would be 1 plus x squared is equal to 4. And subtracting 1 from both sides, we get x squared is equal to 3. And then take the square root of both sides. So the length of that side that we didn't know will be the square root of 3. And this is what we would call our 30, 60, 90 triangle. If you know this special triangle, then you can find the trig function values for 30 degrees and all of the trig function values for 60 degrees. Now when you're looking at this triangle, remember the hypotenuse, the length of the hypotenuse is always the longest. So when I look at these 3 lengths of these sides, the 2 would be the hypotenuse. It's the longest of the 3 sides. Square root of 3 is about 1.7. You could put that in your calculator to find an approximation. But square root of 3 is the second largest, and it's across from the second largest angle in our triangle. And 1 would be the smallest value, and 1 is the side that is across from the smallest angle. So we want to have this memorized so that we can use it to find all of the trig function values for 30 degrees and all of the trig function values for 60 degrees. Alright, so now let's use those special triangles, that special triangle that we formed, our 30, 60, 90, to find all of the trig function values for 30 degrees. So here's my special triangle that we just developed. We're going to take the perspective of the 30-degree angle, and we're going to look for the side that is opposite. We're going to look for the side that is adjacent, touching the angle, and of course the side that is across from our 90-degree angle will be our hypotenuse. So when we go to find the angle for 30 degrees, we want sine of 30 degrees, that will be the opposite side, so that will be 1, divided by our hypotenuse, which is 2. So sine of 30 degrees would be 1/2. Cosine of 30 degrees will be the adjacent side, square root of 3, divided by our hypotenuse, which is 2. So the cosine of 30 degrees is the square root of 3 divided by 2. And tangent, that is the opposite side over the adjacent side, which is square root of 3. So 1 divided by the square root of 3. And of course, we are going to find the rationalized version of this. So the tangent of 30 degrees will be square root of 3 divided by 3. Now we will find the reciprocal function values. If sine of 30 degrees is 1/2, then cosecant of 30 degrees will be 2. Remember, these are reciprocals. Secant of 30 degrees will be the reciprocal of cosine of 30 degrees, so we will do 2 divided by the square root of 3, and we will rationalize. So we get 2 square root of 3 all over 3. Put these in little boxes here. And finally, cotangent of 30 degrees will be the reciprocal of 1 divided by the square root of 3, and that will just be the square root of 3. So we don't have to necessarily have these memorized. If we know our special triangle, then we can work from the perspective of a 30-degree angle and develop all 6 trig function values. Now let's do the same thing for 60 degrees. So we're going to take that same 30, 60, 90 special triangle, and we're going to work from the perspective this time of 60 degrees. So the side that is opposite of our 60-degree angle will be square root of 3. The side that is adjacent will now be the 1. That's the side touching our angle, and our hypotenuse is still the side across from our 90-degree angle, that's still 2. So sine of 60 degrees will be opposite, square root of 3, divided by the hypotenuse, which is 2. Cosine of 60 will be the adjacent side, which is 1, divided by the hypotenuse, which is 2. So cosine of 60 degrees will be 1/2. Tangent of 60 degrees, we will do opposite, square root of 3, divided by the adjacent, which would be 1. So we really just get square root of 3. And now we will work with the reciprocal function values. So cosecant of 60 degrees will be 2 divided by the square root of 3. And we will rationalize. So we get 2 square root of 3 divided by 3. Secant of 60 degrees will be 2, reciprocal of cosine, and cotangent of 60 degrees will be 1 divided by the square root of 3, and once again we want to rationalize, so we get square root of 3 divided by 3. Now if we compare these, once again we can see that since we're working with the same right triangle, that the cofunctions of these angles are the same. So if I look at sine of 30 degrees, sine of 30 degrees will be the same as the cosine of 60 degrees. These are what we call cofunctions. If we're working within the same right triangle and we're working from the perspective of two separate angles, their cofunction values will be the same. Let's look at another one. Tangent of 30 degrees should then be the same as cotangent of 60 degrees, and we see that they are the same. This is why we call them co-functions, because they're angles that add up to be 90 degrees within the same right triangle, and their co-function values will be the same. To find the trig function values of 45 degrees, another one of our special angles, to find this we need to develop another special triangle. And we're going to use an isosceles triangle. And an isosceles triangle means that we have a 90-degree angle here. We have two of our sides that are exactly the same. So I have exactly the same angles, and the lengths across from them are also exactly the same. So we need to figure out what is the length of that third side, and that will be, well, we have 1 squared plus 1 squared, and we are looking for the hypotenuse here, so we'll call that x squared. That will be 1 plus 1, which is x squared, 2 equals x squared, and then take the square root of both sides. We get that this side will actually be a length of the square root of 2. So, it doesn't matter which 45-degree angle we use, we will use one of them, and we will work from the perspective of this 45-degree angle. So, the side across from it will be the opposite. The side next to that angle, touching it, will be the adjacent side, and the side across from our 90-degree angle will be our hypotenuse. Now to find the sine of 45 degrees, we need to find the opposite over the hypotenuse, and the opposite side would be 1. The hypotenuse would be the square root of 2, and we want to rationalize, and so our final answer here would be square root of 2 divided by 2. Cosine would be adjacent over hypotenuse, and that would be 1 divided by square root of 2 again. And when I rationalize, we get square root of 2 divided by 2. So sine and cosine are exactly the same for a 45-degree angle. Tangent of 45 degrees, that will be opposite over adjacent. Opposite side would be 1. The adjacent side would also be 1. So tangent for a 45-degree angle will be 1. Now when I go to work with my reciprocal function values, sine was 1 divided by the square root of 2, so cosecant of 45 degrees will be the square root of 2 divided by 1, or just the square root of 2. Secant of 45 degrees, the same thing, 1 divided by the square root of 2, so that would be square root of 2 divided by 1, which is just the square root of 2. So cosecant and secant of 45-degree angles are the same. Cotangent, of course, would be the reciprocal of tangent, so that would be 1. Notice that tangent and cotangent are exactly the same. The reason why they're the same is that we are working within the same right triangle, and you notice that if this is 45 degrees and this is 90 degrees, then this has to also be 45 degrees. So cofunctions of angles that add up to be 90 degrees are within the same triangle, cofunctions will be the same. So sine, we said, was the same as cosine. These are cofunctions of angles that add up to be 90 degrees. Cosecant is the same as secant, and cotangent is the same as tangent. So cofunctions of angles that add up to be 90 degrees will be the same. Throughout this video, we have mentioned the word cofunctions. And cofunctions would be like sine and cosine, tangent, and we have cotangent, secant and cosecant. If we have a right triangle, then that means that one of my angles is 90 degrees. Within any triangle, the sum of all of the angles must be 180 degrees. So what does that tell us about the sum of the angles A and B? Well, A and B have to sum up to be 90 degrees. Now, something special happens when we are talking about the trig function values of angles within the same right triangle. So I have A and B. So let's look at the sine of A using just the definitions of the sides in terms of A and B. So if I'm looking at the sine of A, let's see, you start here from this perspective, that would be opposite, so that would be A divided by the hypotenuse, which would be C. Cosine of angle A would be the adjacent side, which would be B divided by the hypotenuse, which would be C. Now if I have exactly the same right triangle, but I'm working from the perspective of the angle B, and I want to find the sine of that, well, since we're working within the same right triangle, we notice that we're using the same sides, the same lengths, the same sides. So across from angle B is side B divided by the hypotenuse, and then cosine of B would be the adjacent side, that would be A divided by the hypotenuse, which is C. So when I'm working with angles in the same right triangle that add up to be 90 degrees, their cofunction values will be exactly the same. So sine of angle A will be equal to cosine of angle B. And vice versa, cosine of angle A will be equal to the sine of angle B. So we want to develop what we call the cofunction identities. When are cofunctions equal to each other? Well, we can say that sine A is equal to, and let's rewrite this little equation. We have A plus B equals 90 degrees. Let's solve for B. So we know that sine of A is equal to cosine of B, but let's rewrite B in a little different way. Let's subtract A from both sides. That gives us that B is equivalent to 90 degrees minus A. This is what we would call a cofunction identity. And all this says is that if the two angles inside of our cofunctions add up to be 90 degrees, then those cofunctions will have exactly the same value. So here are all of our cofunction identities. So for any acute angle A, cofunction values of complementary angles are equal. Remember that complementary angles means these are two angles that add up together to give 90 degrees. That was our complementary angles. So cofunction values of complementary angles are equal. Sine of angle A will be equal to the cofunction value, so equal to cosine of 90 minus A, and so on. So let's write each function in terms of its cofunction. So let's see how we would work with these and how we would use them. Sine of 90 degrees, what would that be equal to in terms of its cofunction? Well, its cofunction would be cosine, and we need these angle values to add up to be 90 degrees. So 90 degrees minus 9 degrees would be 81 degrees. So sine of 90 degrees would be equal to cosine of 81 degrees. So cofunction values of complementary angles will be equal. Cotangent of 76 degrees would be equal to tangent of what angle? So we need complementary angles. So let's say 90 degrees, take away 76. That would be 14 degrees. So tangent of 14 degrees would have exactly the same value as cotangent of 76 degrees. Okay, lastly, we have cosecant of 60 degrees. In terms of its cofunction, what would that be equal to? So cosecant is cofunctions with secant, and we need complementary angles. So 90 degrees take away 60, we end up with 30 degrees. So cosecant of 60 degrees is equal to the same value of secant of 30 degrees. So cofunction values of complementary angles, angles that add up to be 90 degrees, those cofunction values will be exactly the same.